Hi, everyone. So last time we were talking about chapter 7, talking about qubits and sort of the math behind the complex state of a qubit. And we didn't finish the chapter, so we're gonna sort of pick up where we left off and then move into chapter 8 and see if chapter 8 is pretty short, may or may not finish it. Um, so but super briefly, we introduced the quantum bit and we said, okay, um, it's in C2, so you need two complex numbers to represent it. And we introduced this Dirac notation with Braz and Ketz, and perhaps thinking of them as row vectors and column vectors. Although remember, the row vectors, there's a conjugate involved. Maybe that's not super useful yet, but in the next chapter, we're going to start to see some places where we really save on some notation when we start looking at multiple qubits. And so I think there is definitely value to this bracket notation. So in terms of the complex math, we have two complex numbers, and we have our bases, the standard bases, right? They're ket 0 and ket 1. And so we have a constant times ket 0, another constant times ket 1, and the sums of the absolute values of those two have to equal to 1. So the author went through some math, and I've had a chance to kind of like think about this for a week. But there's two equivalences that are shown. So the first thing to understand is that when we have a complex number, a state with two complex numbers, we can think of it as a four-dimensional space. Okay, it requires sort of four real numbers to define this, and that's the true underlying quantum state. But if all we care about is measurement in our standard basis, then basically you're going to have two probabilities, A squared and B squared. And so the reality is you really only have 2 degrees of freedom that you care about when it comes to using a qubit for the purpose of quantum computing. Okay, that's again not to say that those other aspects aren't sort of true and differentiating the quantum state. But so you start with dimensionality 4 when you impose this constraint that the sum of the absolute values, the squares of the absolute values, has to equal to 1, you're down to 3 dimensions. And then you're actually down to 2 when you say that really all we care about is A and B. So one way that we show this extra dimension that we don't care about is that if you have there's a series of equations that shows that if you multiply a qubit state by a complex number C where the absolute value of C is 1, so it's a unit complex number, then it does not change the values of A and B. Okay, and so this constant doesn't change us from the purpose of quantum computing, and any complex number can be written as R e to the phi I, but in this case, because we know that its unit length, R is 1, we can just drop that. And so any complex number that can be written as e to the phi I does not change our probabilities. E to the phi I can also be written as cosine phi plus I sine phi. So then the next thing is, if you sort of work through the math and you say that the complex state psi is something times ket 0 plus something times ket 1, you can write them in polar notation. So R1 e to the phi I plus R2 e to the, I guess, phi 2 I times ket 1. Now that we know that we can multiply by any e to the phi I, basically what we can do is we can multiply by e to the negative phi I to get rid of that one over here, so that all we're left with is R1, a real number, no complex, no imaginary portion of it. The other thing we can do is, if R1 I don't know if it's already done or not, but if R1 happens to be negative, we can also multiply both by -1. And that's also a unit number, right? So that basically R1 can be forced to be a positive number, and then we have a new phi over here, which has been modified, but there is some other phi that you could say plus R2 e to the phi I. And so this expression over here is not the same, is not mathematically the same as the original one we had with two complex numbers, but it will have the same a squared and b squared, the same probabilities, which from the quantum computing perspective is all we care about right now. So that's what we did here. So the thing that I kind of came to terms with is that if you have a positive real number in front of ket 0, that's basically just the square root of the probability of measuring 0. Okay, because R1 squared is going to be your probability for if you measure this of getting 0. So the fact that we went from this complex number times ket 0 to now a positive real number, we've sort of simplified. So, and then what's the probability of measuring a 1? Well, it's just gonna be 1 minus R1 squared. Okay, so so that's one benefit of having sort of this notation. Now, in addition, we can sort of look at this whole business of e to the phi I, and then ultimately we can rewrite this further as R1 is the cosine of some angle. We know it's a positive number, so it's cosine of some angle between 0 and 90 degrees, between 0 and pi over 2. And so we can say that, hey, this is cosine of a theta that's between 0 and pi. I don't know why they do the half thing, but anyway, a cosine of a theta that's between 0 and pi, but theta over 2 is between 0 and pi over 2, between 0 and 90 degrees. So this is a positive real number. This is a positive real number. Sorry, this is a sine. So this is a real number, but it could be either sine times e to some phi I. And then if we say we've now parameterized this in terms of, instead of R1, R2, and phi, we've parameterized this in terms of theta and phi. Then when you have two angles, theta and phi, you can picture them on a sphere. So that's where I think Maya said last week, spherical coordinates allow you to picture this on a sphere. And that's this block sphere that we're using. So all right, so let me just pause there. That was part recap, part like my additional sort of grokking with why do we do this particular transformation? Because ultimately, most of the time, we're going to be measuring our standard basis, our computational basis, and we want to know what's the probability we get a 0. And so the probability is just going to be, in this case, the square of cosine theta over 2, or if you picture the block sphere, said more simply, it's just how close to the North Pole is it? Okay, if it's all the way at the South Pole, theta equals pi, then basically we get a 0 because cosine of 90 degrees is 0. If it's halfway on the equator, then it's a 50% probability once we square it. And if it's all the way at the North Pole, then it's 100% probability we get a 0. All right. So let me pause there, see if there's any questions. Is that if that's sort of helpful in terms of why we did these manipulations to take something that's two complex numbers, but particularly to represent it as a positive real and a complex number in this particular format so that we can have two angles, a theta and a phi.
I just want to add something to this. I'm not sure that it is helpful, but maybe it is. Multiplying by complex number with length equals 1, like a radius equals 1, like this e to the phi I in the second line. It is actually rotation. So the idea is that if you have a complex number, then you can rotate it in such way that real part will be along x-axis.
Yeah, I think that I understand that it's clearly a rotation. I just can't in my head wrap around how do you rotate in 4 dimensions. So I don't quite know. But yes, basically we're rotating it such that we only have a real component on the x-axis, and that's this R1, otherwise known as cosine of theta over 2, a positive real number between 0 and 1.
Yes, the idea here is that we need formulas for the rotation because we work in 4 dimensions, as you said, and it is really hard to see stuff in 4 dimensions.
Yeah.
So we need to rely on formulas.
Awesome. Thanks, Maya.
You're welcome.
Yeah, thank you for that recap, Ted. That was definitely helpful.
Cool. Thanks, Kirk. All right. And so then as we get into talking about the gates, we are going to mostly do all of our math in C2. So we're going to be using 2x2 matrices of complex numbers. But our intuition is going to mostly be on the block sphere. Okay. So that's kind of where we're headed. So section 4, we talked about, gave the example of you can do a 1-to-1 exact mapping. Oh, I'm getting some background noise. All right. We can have exact 1-to-1 mapping between a circle missing a single point, in this case the unit circle, and a line, in this case the line y equals -1. So we said this is not a linear 1-to-1 mapping. It's not a linear projection. Okay, it's stretchy, where the points at the top of the circle get stretched very far. The points at the bottom are sort of closer to linear, right? And so that was just an example of a way in which you can do 1-to-1 mapping between different points, but that's not in a linear fashion. And so this block sphere that maps complex points in C2 onto the points of a sphere is a many-to-one mapping, and it's definitely not a linear mapping. But using this notation that we had before, where we have cosine of theta over 2 plus sine theta over 2 e to the phi I, that allows us those two angles to define a point on the surface of the unit sphere, such that we can say this point is equivalent computationally to the original complex number. All right, so with that, we now have sort of the z-axis of this block sphere, which is the north and south poles. And even though somebody asked a really great question, so even though the ket 0 and ket 1 in the complex C2 space are orthogonal, because this is a non-linear mapping, they get mapped to the north pole and the south pole. So they're sort of, I don't know how to say it, but like in a line, you know, on opposite sides of the sphere, right? So they're no longer, in that sort of intuitive sense, you know, orthogonal. And it goes to show also that if you look at plus and minus, and you look at what were they, I and negative I in the original C2 space, they also map to opposite points. So it looks like orthogonal points are getting mapped to points that are opposite each other on this unit sphere, this block sphere. So definitely when we're looking at the sphere, we have to have a different intuition than in the original C2. You can't think about orthogonality in the original sense. Now we're just thinking about points on the sphere. Let's see here. I think that's it in terms of then being able to get into the gates. So any comments, questions, thoughts before we start talking about the single qubit quantum gates. All right. So if we take a qubit, which again, primarily we're thinking about in C2, but we're conceptualizing on this block sphere. If we take this state in C2 and we apply an operation on it, that operation is going to be a unitary 2x2 matrix. So it's length preserving. The length of the output is going to be 1, just like the length of the input was 1. And the somewhat interesting property of these gates is that unitary matrices are always invertible. So if you know the output of a gate, you can exactly figure out what the input of that gate was. That's not necessarily true in the classic sense if you have like an AND gate. In an AND gate, if you saw the output was 0, you don't know exactly what the inputs are. There's 3 possible different inputs that could have been there. But in this case, we will never have something like that. Given the output and you know what the gate is, you always know what the inputs were. So then we just go through in section 7.6 a long list of different gates, and we talk about what they do in C2 and have a little bit of intuition on the block sphere. So the X gate swaps the 2 coefficients in C2. So if you have A times ket 0 plus B times ket 1, you get B times ket 0 plus A times ket 1. And I believe that, gosh, I don't even remember. I'd have to check the book. But basically, I think this is, yeah, it's called X. It's a 180-degree rotation around the X-axis, which means that the North Pole flips to the South Pole flips to the North Pole. But it also means that the positive y-axis and the negative y-axis also flip to each other. And anything that's all the way at the X or at the negative X will remain unchanged. I don't really know what to call that. The East Pole, as it were, or whatever. The East Pole and West Pole are going to be, you know, unchanged, but the North and South poles will flip and the front and back poles will flip. Okay. And so then we can see the matrix in C2 that accomplishes this is a permutation matrix. So whereas 1, 0, 0, 1 is the identity matrix, 0, 1, 1, 0 is this permutation matrix that flips the 2 numbers. And you can show all these things. You can show it's unitary, you can show all these things, and it does what we're looking for. Basically, any unitary matrix, 2x2 unitary matrix, is a valid operation to perform on our quantum state. Okay. At this point, I have no idea how anybody builds any of these gates, how you would actually say, I want to build something physically that if I have the state, you know, of an electron spin or whatever in my quantum state psi, how do I actually run it through some physical object that's going to perform the X gate and do that? I have no idea. Okay. But mathematically, it's at least simple enough to say we could have a matrix that does this. You can rotate 180 degrees around the z-axis, call it a z-gate. You could rotate 180 degrees around the y-axis, call it a y-gate. The identity gate does nothing. We have this interesting Hadamard gate, the H-gate. I believe the matrix for that is 1, 1, 1, -1, if I remember right. Once again, you can show that it's unitary, it's its own inverse. So if you apply it twice, then you get back your original state. There's other ones where you rotate not 180 degrees So this R matrix, and I don't even remember exactly what the S matrix is. I think it's like you rotate 90 degrees instead of 180 degrees, and so on and so forth. There's another gate they show that is the square root of naught. So again, if you have a 2x2 matrix, well, not all matrices, but in this case, if you have the naught matrix, which is 0, 1, 1, 0, you can calculate there's a matrix that when multiplied by itself gives you that. So it's sort of the square root of that matrix. That was kind of a blitz through. There's a bunch of questions that were in this chapter, and I don't know if anybody tried to do the questions, if anybody had issues. So any questions, comments about either the content or the questions inside section 7.6? Are you guys happy with the idea of we can pass a state through gate and we'll just get a transform state? All right.
I
Cool.
linked something that might be worth just showing for a second if you can pull it up, Ted.
Yeah.
So it's basically I was watching this YouTube video and this guy was kind of showing this, and it allows you to just kind of simulate a bunch of different circuits. And so you can put the Hadamard gate, you can put the NOT gate, you can put the C NOT, and then on the left side, if you click on the 0 cat, you can change the inputs too. And so try just putting a Hadamard gate, yeah, and then hit enter. And then it will show you the A and the B and the matrices, and you can kind of sit there and just play with little circuits and build it out and see what happens with the various different gates. So just a fun little tool if anyone wants to play around with it.
Cool. Yeah, I think this will be helpful, especially as you get to the more complex stuff. Thanks, Ryan.
Yeah, that's neat.
Okay.
So Ted, I would like just to add a little information. I don't know if it's that useful, but could I use the whiteboard here?
I believe you have permission, but let me know if you get a.
It says you cannot use the whiteboard.
Okay, one sec. I apologize, but since at some point we had some rude visitors,
yeah, it's okay.
Locked things down a little bit more. So where is? Hold on. I don't even see. One sec. Okay, I think you can do it now that I'm not sharing.
Let me check. Can you see it, everyone?
Yeah.
Okay, that's good. So basically, I want to say that like the have those like matrices. So just I want to share something about the matrices and how I like to understand them and memorize them if anyone would like to do that. So basically, I see that each column is the new first basis. Like this one is the new first basis for the X, and this one is the new one for the Y. So like it was 1, 0 for the cat 0, and it was 0, 0, 1 for the ket1. So the new one is actually now 0, 1, and the new one is 1, 0. So that's why the X or not X do this not F. So this is something cool I would like to share.
Yeah, that's awesome. That's awesome. So basically, because we're going from one orthonormal basis to another orthonormal basis, they're both length 1. We don't have to worry about scaling. Otherwise, you might have to divide by a constant just to scale it. And so basically, this is just a change of basis. So the Hadamard gate is 1, 1, 1, minus 1. Basically, it's changing to your new basis is 1, 1, and 1, negative 1, but there's like a 1 over square root of 2 scaling factor or whatever. But basically, that's your new basis, right?
Yeah.
And so if you look in the
exactly.
book, 1, 1 is like the plus, I think, and 1, negative 1 is the minus. And again, you might just need to worry about scaling to make sure that everything's still length 1. So then there might be a 1 over square root of 2 times 1, 1, and times 1 minus 1. That's great.
Yeah. So that's something I
Thanks
noticed.
for sharing that.
I just wanted to add to this.
So
Sorry, just wanted to add to this that some of the gates we've seen, they could be equivalented with space transformation in the following way. It could be rotation, and it could be mirroring as well. For example, when we exchange X and Y, it means that we got mirroring along bisectors between X and Y. And by the way, it is true when you add the third axis, Z will be in the same place. Oh no, Z will be swapped too if we just rotate everything around these bisectors. Anyway, it is a unitary transformation. Sorry, we can imagine it as some kind of symmetries and rotations.
Yep. No, that's great. Yep. They're all length preserving. So length preserving operations, they can't be stretches, they can't be skews, you know what I mean? They have to be rotations and reflections in some kind of combination.
Yes.
Yes, and another thing, the center cannot change in linear transformation.
Yes, yes. The 0 is always the 0 in these linear maps. And so that is what's different from if you see some stuff in ML papers, sometimes they do what they call an affine transformation. And so that's a linear transformation, but the 0 doesn't necessarily have to stay the same. So the simplest one would just be x equals x plus 1, right? Or y equals x plus 1, whatever. The new x prime equals x plus 1, right? You shift everything to the right. That is clearly a very linear transformation. It's very simple. Just move everything to the right. But that is not a linear map because the 0 doesn't stay the same. You absolutely positively have to have the origins stay the same. Yeah. And so that further limits you basically to rotations and reflections. Cool. All right, so quick note here that in our circuits, we're going to see this 0 ket reset operation. That is not a gate, but certain quantum computers allow you to simply say, well, I've been tracking on a certain, qubit, certain things, and now I just want to say I want the 0 ket there over again, and that's a legal operation. Let's see here. And then there's this interesting thing that any unitary matrix can be expressed if you say a complex unit times some linear combination of the identity X, Y, and Z matrices. So there's only 4 numbers in a 2x2 matrix. So basically, this is your basis. The identity X, Y, and Z will span all possible 2x2 unitary matrices. I'm not sure what that means. Maybe there's some deeper connection, but basically, it does sort of speak to the fact that we showed a lot of these gates, but you don't necessarily need all of them in your quantum computer, because some of them you could get in multiple steps by composing some of the other gates. And so at least that's one takeaway. You don't need every one of these. Well, theoretically, there's infinitely many unitary matrices, so you don't need all of them. You just need a certain core set, and from that you can use those as building blocks to. It may be more convenient to do things in one step, but worst case, you could do the same effect in multiple steps with different kinds of gates. All right, so that kind of wraps up chapter 7, the single qubit gates. Any other questions, comments, clarifications? All right.
I think the gates is one of the parts that I understand the best now, but I think we'll have to see. I've said this multiple times, but I'm interested to see what this turns into mostly, because like in normal programming, you have your OR and your NOT and your various other gates that you might actually use often, and it's a bit more abstract to me to say, why would I use a Z gate or something like that?
Yeah.
At that level, like choosing to do
I agree.
those things.
Yeah, I agree. I'm waiting to see what exactly are we going to put into memory, into a quantum register, and what gates are we going to shove that through in order to then wind up with something different that actually helps us, right? But yes, in terms of doing the math, it is a little bit different. It's a little less intuitive than classical gates, but nevertheless, I think, at least for me, I've done enough math that you just say like f of x, right? Y equals f of x. In this case, x is a vector of length 2 complex numbers, and y is a vector of length 2 complex numbers, but it's still the case that y equals f of x. In this case, f is always invertible. Okay, I can work with that. I still don't know where you're going with this, what problem you're going to solve, but I can work with that. So yeah, thanks, Ryan. All right, so chapter 2, there was a bunch of stuff. I only wrote down some of it, but basically, once we have 2 qubits in a system together, and again, this system is still expected to be completely isolated from the rest of the universe, whether that's in real life 100% possible or not. Conceptually, these 2 qubits are sitting there inside this black box, and they're not interacting with the entire rest of the universe at all. How do you represent the state space when you have 2 qubits, not just 1? So they introduce the tensor product notation and the idea that basically you're going to constantly multiply by the dimensionality of everything you add to the system. So if 3 qubits is an 8-dimensional system, and you take another 3 qubits, another 8-dimensional system, and you put all of those together into one system, you're not going to get 8, you're not going to get 16, you're going to get 8 times 8. You're going to get 64 dimensions in your new quantum system. And so since a single qubit is 2-dimensional, basically, it's always just going to be 2 to the n, where n is the number of qubits you have in your system. And so this is kind of interesting. This thing is going to grow very quickly. If you have, a 10-qubit system, then, potentially you have 1,000-dimensional quantum space. So there's a lot of room in this 10,000-dimensional space. So we've got our I don't know how you're supposed to say this, the name of this symbol. It's a time sign
It is a
inside a
tensor
circle.
product. It is called
So it's a tensor product, but I'm just saying
Yes.
sometimes you see this in books representing other things like a circle, a plus in a circle, or times in a circle. But so when you see this times in a circle, here we're using it to mean tensor product. And so early on, you see the notation where we're talking about a vector space capital V tensor product with a vector space capital W. And the new vector space is the tensor product of those two vector spaces. And if they're dimension n and m, then the new space, that's the tensor product of the two, is n times m. Mostly in the rest of this chapter, we'll be talking about individual vectors. So this is V tensor product with W. These are individual vectors. This is no longer talking about an entire space. So there's a bunch of nice properties like associativity with addition. If you look at sort of the norm of V tensor product W, it's just the norm of V times the norm of W. Tensor product plays really nice with matrix multiplication. So if A, B, C, and D are matrices, could be of any size. You can assume 2 by 2 for the purpose of this, but they could be anything. Then A tensor B quantity times C tensor D is going to be the exact same thing as A matrix multiplied by C, A times C, tensor product with B times D. And very quickly, if you do the math, you will also see that the dimensionality certainly fits. Okay, so if these are all n by n matrices, then this tensor product is an n squared by n squared matrix, as is this. And in this case, with regular matrix multiplication, two n by n matrices multiplied by each other, still an n by n. But then when you tensor these two products, once again, you get n squared by n squared. So that's a quick check. If A and B are unitary matrices, then A tensor B is also unitary. This is going to be kind of important because we're going to do composition of single qubit gates, and we want this composition to be basically a multi qubit gate, and of course it has to be unitary. So so good thing there, good sanity check. All right, so that's the basics of I definitely didn't explain everything. I hope people had a chance to read the book, but that's the basics of how our vector space is going to grow when we add qubits, and how basically we're going to use the tensor product to, I don't know how to say it other than to tensor product together to individual states, whatever. So if we have a qubit with state psi1, and we have another qubit with state psi2, if we shove those into a system together, then the new state is going to be 4-dimensional, and the value of that is going to be psi1 tensor product psi2. We're always just going to do the tensor product of our individual vectors, our individual kets. Anything to add? Any questions? All right. So then the next thing is section 8.2 talks about entanglement. And see, this is where I feel like the author has strengths and weaknesses. So basically, we've shown that if you take two qubits, you can just sort of tensor product them together. And you're going to wind up then with a 4-dimensional vector. Okay. Basically, what he says then is, if you have a 4-dimensional vector and you can represent it, if it equals the tensor product of two 2-dimensional vectors, then that's a separable state of 2 qubits. If you can't represent it as the tensor product of 2, then this is an entangled state. And in some ways here, again, I feel the strength is this mathematical definition is very black and white. You don't need any intuition around what the heck does entanglement mean, and is this physically intuitive that 2 electrons could be entangled or not, or whatever. It's like, no, it's really black and white. It's, hey, look, if you bring the 2 of them together and you can show that it's just the product of these 2, they're separable. If not, they are in some way entangled, and the results are in some way interdependent. So I threw in this personal note here. I say personal note because I don't know if this is 100%, accurate, but I find this kind of analogous to the idea of probability distributions being either independent or dependent. Okay, so if the probability of 2 events happening is just, you multiply the individual probabilities together, then that means that those probability distributions are independent. Okay, and if there's any dependence between the 2, then the probability is not always going to be just multiplying the 2 of them together. And the other thing with that is that just because 2 probability distributions are dependent doesn't mean that they're utterly 100% dependent, such that if you know the value in one, you know the exact value in the other. That would be the case if you had correlation of 1 or -1. But as we've seen, sometimes you can get just slightly correlated distributions where basically, if you know the value of one, then sort of the range of the other one has tightened, but it's not like you just bam, know the full value. So in the same way, the example in the book shows, like the first example shows like complete entanglement, where if you know the value of one, you know the exact value of the other one, but you can have less than 100%. Again, I don't know if this is a technically right way to say it. You can have less than 100% entanglement, just like you can have 2 probability distributions that are not 100% correlated. So that's my personal intuition. If that works for you, great. And if it doesn't, then disregard it.
I think it's a very nice analogy.
Thanks, Maya. All right. Any comments or questions about entanglement? All right. So this is the flip side. The weak side of this is the author gave a very clear mathematical definition that really has no gray, no questions, no weaknesses, but also the author did nothing to motivate why the hell do we care about entanglement at this point. And so ultimately, we're going to show that we're going to see that we need entanglement in order to do things more powerful with multiple qubits than we can do with a single qubit. Without entanglement, basically, you're just doing a bunch of single qubit operations and you're not really growing. So that's the super layman's motivation for that. All right. Also introduced these 2 qubit states, our capital phi plus, capital phi minus, capital psi plus, capital psi minus. Any questions about these entangled Bell states? I think we're going to see them more. Okay. So then let's see here. Did I skip over the? Oh, okay, yes. So then also in section 821, the author shows how in the Dirac notation, we simplify a lot of things. And so, for example, if we have ket1 tensor product with ket2. We could show like a lot of full notation, but ultimately what we do is when we have multiple kets together, we drop the intermediate symbols, all the extra bars and angles and whatever, and we just jumble things together. So you can have like, you know, a bar 0, 0, 0, 0, 4 zeros, and then a closing angle bracket. And that's a lot fewer characters to say than if you fully wrote out, you know, the ket, tensor product, ket, tensor product, ket, you know, with all the bars and all the angles and all that kind of stuff. So hopefully that notation is reasonable. And then if you have a really long binary string, sometimes that's a nuisance. So he showed, for example, instead of a length 8 binary string, you can convert the binary number to decimal, and you can just say, oh, 215 with this is a little subscript 8 is really a length 8 binary ket, but we just didn't feel like typing it all out, and so we just wrote it in decimal. All right, the mysterious density matrix that we saw with 1 qubit, he shows it once again here with a multi-qubit system. So if this psi is now, let's say, 2 qubits, so it's a length 4 complex vector instead of length 2, the density matrix is still just ket psi outer product with bra psi. And so then this will give you a 4x4 matrix, which we'll call rho. This is our density matrix. And he mentions that, hey, it's always Hermitian and positive semi-definite. And this one I'm a little bit less sure of, but I made a loose analogy between independent and dependent probability distributions. And so I'm also going to say, if you have 2 probability distributions and we're thinking about to what degree are they dependent or not, we can use a covariance matrix in order to describe those 2 probability distributions, right? And so if you have zeros off diagonal, then they're all completely independent. And likewise here, if you have a density matrix and you have zeros off diagonal, then basically you have a pure state, I believe. But as soon as you have other things, then that means that there's a level of independence of dependence between these 2 probability distributions. Again, I'm not sure if this is a perfect analogy, but once again, I feel like the idea here is just to get some intuition that you either have sort of a pure or you have more of like a mixed state here with this density matrix. All right, now we're going to get into the gates. So the matrix for a single qubit gate is 2 by 2. Now it's going to be 4 by 4. Again, these are 16 complex numbers, a 4 by 4 matrix of complex numbers. And the author gives some examples. Again, no motivation as to why these particular examples, why we would want these, why these are useful. But so the first is, what if you applied the Hadamard gate to each qubit in a 2 qubit system? So again, we're not technically doing anything complex. We're just applying H to each of them individually. What is the output of that? So the output, again, of a multi-qubit system is just the tensor product of the individual ones. So the sort of length 4 vector of this is just going to be apply Hadamard to psi1 and tensor product that with applying Hadamard to psi2. And then, you do a bunch of math, you work things out, and you get some numbers, you can figure things out. And so the author shows basically it's got a bunch of ones and a few negative ones in there. And you can actually sort of thinking of it recursively that, again, the H is like 1, 1, 1, negative 1. And basically, if you want to know what's going to happen in a bigger system, if you just simply write the n-1 Hadamards, and you put sort of an n-1 Hadamard, an n-1 Hadamard, an n-1 Hadamard, and then the negative of that, then you get a twice as big matrix, and it's all ones and negative ones, and that's the new. So you can build it up recursively. So again, this isn't saying sort of what the purpose of a bigger Hadamard is, but I feel like, again, in terms of like the pure math, it's just showing anytime you want to know what's happening in a multi-qubit system, just tensor product what's happening to each of the individual qubits, and you're good. All right, we've got this quantum swap gate, which I had to reread it several times. It was kind of confusing to me. But the idea is that, gosh, I don't know how to say this. If you have two qubits and your the idea is you're sort of swapping the two of them. I don't think you're literally swapping the two of them, but you're producing an output that is computationally the same as swapping the two of them or whatever. So the really important cases are when one of them is, to the extent that one is 1 and the other is 0, or the first one's 0 is the other 1, because when they're the same, then you get your 0, 0 and your 1, 1 bases in your new space. So the end result is that you have this permutation matrix where in a normal identity matrix, you'd have ones on the main diagonal, and the second and the third columns are basically swapped here. And actually, just like Karam said, you can just think of this as being the new 4 columns in your new basis. And so you can see the new basis, the second basis is what used to be the third column, because the one's down here. So that's another way that you can think about this. So there's a swap gate, and then I didn't try to paste pictures or draw pictures, but in the book you can see that the line has X's on it. The quantum C0 gate, I think, gets used a lot, so this is an important one. So the idea is that the second qubit will get flipped if the first qubit is a 1, and it will not get flipped if the first qubit is a 0. Just to be clear, the first qubit doesn't have to be all the way 1 or all the way 0. So if it's like, 3/4 1, then it's sort of 3/4 flipped, 1/4 not flipped. But at least for my brain, it's easiest to think about what happens when it's 100% ket 0 or 100% ket 1. And then just a note that if you think about the classical concept of a control and sort of like an output gate, the C0 does not work like that. There are weird examples you can show where you can sort of think of the control and the output as being interrelated, but not in the sense that the control is the one doing all of the work and the other one's the one that's all changing. You can sort of change perspectives, and then it looks like actually it's the other one that's staying the same, and the control's is the one that's getting modified. So I don't know how to say it other than that. It's just that the classical idea of a control not being modified is not exactly what's happening with the C0 gate. That's the standard way of thinking of it, but it gets more complicated than that. And then we have a few others. You can do controlled Y, controlled Z instead of controlled X. You could also do a controlled whatever, rotate by some angle other than 180 degrees. And there's 2 descriptions of gates that have 3 inputs. The Toffoli gate or the CC0 gate. It basically has what you think of as 2 controls. They both have to be ket 1 in order to flip the third qubit, apply X to it. And then there's this C swap or Fredkin. I don't know if Fredkin's used. I've seen Toffoli used. But the C swap gate basically says if the first qubit is ket 1, then it applies the swap gate to the other 2 qubits. And again, notes on the pictures of these. So based on these concepts, you can create your 4x4 unitary matrix, or in the case of these last 2, your 8x8 unitary matrix. And what will always be true is that if you take your original input states and you tensor product them, so in the case of the 2 input gates, you tensor product just the 2 of them and you get a length 4 ket. Then you take that length 4 ket, you multiply it by the 4x4 matrix, you get a new length 4 ket, length 4 column vector. That's your output. Whether or not you have any classical intuition as to what the heck happened in there, the math is the math is the math. Tensor product to your individual qubits, multiply by the matrix, you get a length 4 ket. Okay, so I think that's probably the strength of the author's approach, because sometimes if you try, I think in other books, if you try to give too many real world analogies and you say, well, you know, in this case, the quantum X gate is a little bit like a farmer who's got some pigs and whatever, there's always going to be some place where that analogy breaks down. Okay, but in this case, it will never fail you. Just tensor product your inputs, multiply by the matrix, and you get the right answer. So, all right, let me pause here to see if you guys have questions, comments about the multi-qubit stuff.
Yeah, so thanks a lot for those explanations. Actually, I've read this part and I had a lot of questions, but now I understand a lot of more things. But the concept of wires, well, what is it? I can't understand it a lot.
Oh, wires. Okay, yeah. So the author hasn't talked about this at all, even though he's shown some gates and like a horizontal line, and here's this black box or whatever. In a regular circuit, you know, we have this concept of wire, and the intuition on it, whether that's how it's physically implemented or not, is that if we have a signal on a wire, let's say it's a 1 or it's a 0, that it'll move from point A to point B and it will be unchanged. That if it started as a 1, it'll stay a 1. It's a 0, 0. Okay. In this case, we're not really talking about physically moving our value, but it's kind of more thinking about keeping track of it in time. Okay, so imagine a super simple circuit where we've got 2 qubits, and the first qubit we pass through an X gate, and the second qubit we just don't do anything to it. So what we'll see is that that circuit will be drawn with a complete horizontal line for the second qubit. And that means that just the value will be perpetuated unchanged through time. Whereas at some point, the first qubit is going to pass through this X gate, which does its thing, which in this case we know is it's flipping the 1 and the 0 probabilities. And then from then on, that horizontal wire that comes out of it represents that from that time on, it is unchanged. Okay, so you can think of a quantum circuit diagram as representing time left to right, and that time is moving from left to right. I don't know in the Zoom if it looks like left to right or right to left because of this mirroring business, but anyway, you can think of on the paper as time is flowing from left to right. And it's not always necessary to think of it literally this way, but when you've got gates kind of lined up vertically, you can think of, okay, these things are happening to my different qubits at the same time. And then my transformed outputs are going to remain unchanged as long as I see just straight horizontal wires. And then at a certain point in time, a transformation will happen. And again, I have absolutely no idea how you would physically build an X gate or an H gate that affects a particular electron or a particular atom or a particular whatever. But at this point, we're not even dealing with, I think the last chapter in the book starts to talk about how would you actually build one of these suckers. At this point, we're just talking about, imagine mathematically you could do this. Can we then devise algorithms that will produce some sort of useful computation, and then we'll challenge the physicists to actually make us one of these suckers? Does that help?
Yeah, totally. Thanks a lot.
Any other comments, questions?
I just want to remind people that tensor about which they're talking about has nothing to do with tensor. Well, it has a little bit, because it deals with the matrix too, with something we studied when we read PyTorch book. So I remember you had a whole speech about it, by the way, how it is different in mathematics.
Yeah,
And
yeah. I actually saw somebody on Twitter did something where they said something like, "Oh, we deal with all these tensors in PyTorch and TensorFlow, and so I'm linking you to like a textbook that I think is very useful." And it was a mathematical tensor calculus or whatever. And I was like, no, tensor calculus has nothing to do with TensorFlow. It may be useful to know the math, but no, it's not the same tensor. It's a different tensor.
We have matrices there, and you have matrices over there too. It is just structures are different, which we do with the matrices.
Yes. So in this case, we are truly doing a mathematical tensor product.
Yes, and we got tensor spaces, by the way. I don't know if they mention it or not.
Thank you. Actually, I don't even know. I don't know, like a GPU or PyTorch, can you even just say, I would like the tensor product of these two matrices? I don't know. I don't think you can. I don't know, maybe. Doesn't seem particularly useful for computer graphics or for neural networks. So I don't know that NVIDIA would bother implementing a tensor product in their graphics cards, in their GPUs.
And again, as a former educator, I have something to say about the way they present material, but it is of course no use here because I cannot change the book. So I will just express my sympathy and gratitude to our presenter for going through this.
Thanks, Maya.
Yeah, definitely second that.
Yeah, and again, I haven't seen enough to say that there's a book that I would recommend over this one. So don't take the criticisms too severely. Maybe at some point I'll read another book and I'll say, okay, I actually recommend this one over. But also, I need to reserve judgment until we get to the end to see maybe it all comes together beautifully. It's like, oh, that was awesome. All right. Any other questions?
I don't necessarily have a question, but I was kind of just expanding out of the book yesterday, just saying like, what else can I learn about this stuff? And I was reading through the Wikipedia page, and it was kind of interesting seeing like what is actually the state of things, because this book is, I think it's a couple years old at this point. So I was just kind of checking on like how many qubit computers do we actually have and stuff like that. And it does look like D-Wave has something that they released that's like 5,600 qubits. So it's further along than I expected, because we've talked about 38 and 100 and stuff like that, but not in the thousands. So I thought that was kind of interesting. But I still I don't know. It's interesting to think about, but I don't really understand how that machinery operates. Not that I have the deepest knowledge of processors and GPU circuitry either, but it's just kind of interesting to think about, like how does this even work? What should I be thinking about in terms of quantum computers. Because in my head, at least the way that we've been learning things, I almost view them as like a FPGA, where it's like, this is something that I can arrange various circuits onto, but it's different from like a CPU that might have like a very fast integer addition operator or something like that built onto it. But yeah, that's kind of the stuff that I've been looking at.
Yeah, I'm crossing my fingers that it's going to get interesting. I mean, we know that there's at least a few algorithms. There's that whatever Shor's prime factorization algorithm. So I know there's at least like a few really interesting things. And so it'll be interesting to see the problem setup.
Yes, how exactly they managed to implement all of it. I'm curious about it too.
Yeah. All right. Well, we're a little bit early, so we may end up just taking a pause before the next meeting, but maybe let's end the recording here.